Hi everyone, it's great to have the opportunity to present my ongoing PhD project, which is looking to improve ISFET-based diagnostics using integrated electrode systems. And the chair of the AMR review set up by the UK government a few years ago puts it best when he says that rapid and portable diagnostics are the most valuable tool that we have to curb AMR by giving clinicians the information they require to make better decisions about antimicrobial administration based on diagnostic data that is provided then and there. At the Centre for Bioinspired Technology, we've been working for the past decade on using ion-sensitive field effect transistors, or ISFETs, as diagnostic technology. And these are ideally suited to form rapid, portable, but also accessible diagnostic devices based on the same microchip technology that powers your smartphones. So these ISFETs are a little like chemical cameras, but instead of detecting light, they detect charged hydrogen ions. So how we detect DNA is based on an isothermal amplification reaction that replicates DNA and by doing so produces hydrogen ions that these ISFETs can detect. And we can pack thousands of these sensors onto a small chip. The specificity of our device stems entirely from the reaction chemistry that we use for the amplification. Now, currently, with our sample solutions, the DNA is randomly distributed throughout. If we could draw DNA down towards the ISFET surface, then when hydrogen ions are produced during amplification, then these hydrogen ions are more likely to be detected and will be detected quicker. So we can improve the speed and sensitivity of our device through DNA manipulation. We think that electrodes are naturally suited for this task as they can be integrated into the same platform as the ISFET and in the same fabrication process. These electrodes can manipulate DNA using a force known as dielectrophoresis, or DEP. Now, we may be most familiar with electrophoresis, which is the electric field acting on the fixed charges of the DNA molecule, whereas DEP is an interaction with the electric dipole, or separation of charges of the molecule. And this DEP force will move DNA down towards regions where the electric fields are strongest, i.e. the edges of electrodes. So to test this hypothesis, we've developed a small microchip that contains 3 5x2 ISFET arrays interspersed with electrodes. These electrodes come with 3 different geometries that have slightly different DNA trapping regions and electric field strengths. So by comparing the geometries, we can use that information for future iterations of the chip. Now, I use the finite element method software, COMSOL, to estimate the electric field strengths that these electrodes would achieve. And that showed that for all 3 electrode designs, we could achieve trapping at a low voltage of 1.8 volts. That is also the maximum input to the chip. Now, we've had a few delays in getting this chip back to us. So in the meantime, I've been wondering if we can estimate the effect that this DNA manipulation would have on the signal of the ISFET. And to do this, I would need sort of a rather novel simulation method that takes into account the spatial dependence of the DNA amplification reaction. So DNA amplifies as a spherical cluster that has a fixed position and grows with a fixed rate of radius increase. The hydrogen ions that are produced during the application reaction are produced at the surface of the cluster and at a rate that is proportional to the cluster surface area. We can sort of account for this proportionality using data from past reactions we've run with a known pH change. So the best way to illustrate my implementation is through a animation. And I used COMSOL with a level set method Now, the level set method takes the two different phases of the reaction, DNA and water, and represents them as a field that varies between 0 and 1, with 0.5 being defined as the surface of the DNA cluster where the hydrogen ions are produced. The simulation also includes surface reaction chemistry that sort of simulates the pH sensitivity of the ISFET. There's more work to be done in terms of validation of the simulation method, but some early runnings of it show that we can get a signal that is roughly 30% stronger and 3 minutes quicker, which would be a great result for our final device. So to conclude, rapid diagnostics are an invaluable tool in fighting antimicrobial resistance, and ISFETs are well placed to form the diagnostic technology. These ISFET-based devices can be improved with electrode systems to manipulate DNA, and we have developed a prototype microchip backed up by simulations to look at this hypothesis, which this chip will come back soon, so watch this space. Thank you very much.